going to talk about fracturing and fragmentation of rocks in the dynamic range. Quite many people involved in that. A very large part of it, the first half, would be primarily based on the work of Amir Sagi, collaborators in the University of Oklahoma, and Eric Green that passed away last month. It all started almost 20 years ago when Amir Sagi did his master's degree, and we worked on joints. Tensile fractures in geology are called joints in the Dead Sea area, and we went in the streams there and starting seeing joints that usually are assumed to be smooth and planar, and we started seeing something very weird. Showing here, this is a map of that one, scale of 1/4 of a meter with quite many branches. Then we did some experiments in plexiglass and epoxy, and we got very similar structure. This scale is 10 millimeters, and we didn't really know what's going on. And then obviously we were told that somebody in the campus knows what's going on, and from there we decided to check on him. So basically, I'm going to talk a little bit about rates on Earth, of the formation on Earth, and then two topics. One of them is dealing with shuttle cones, which is based on the PhD of Amir, and then talking about mechanisms of weakening of faults, particularly emphasis on earthquake conditions, and this is a work that I'm doing in the last 10 years or so. So this is a very crude schematic view in which this is dimensions of the features, and this scale is the velocity and strain rate, very loose definitions. And this is in geology, so this is the range of slow motions of the strain rate of 10 to the minus 14 or so, which is typical to tectonic deformations, jointing falling in here. And there is the range of a high velocity or fast processes going to the limit of shock wave propagation that occurs during meteorite impact, and this will be the first topic. And then I will talk about the three yellow regions. One of them is the shuttle cone fracturing, where the rupture propagation is on the order of a few kilometers per second, earthquake rupture, which is also on the same order in the front, and earthquake slip, which is on the order of a few meters per second. So we'll look at what's going on at that in these conditions. So let's go in what's going on in the meteorite impact. They basically are meteorite or any extraterrestrial body reach the surface at very high velocity of the escape velocity. This is a model of J. Melosh, one of many by him, who analyzed that, and basically we generate a shock front with excavation, including fragmentation and melting and evaporation of the rocks. And this could be very large, as I'll show you in a minute. This is from experiments done in impact experiments that done in Caltech by Tom Ahrens and others. For scale, this is about a 20 centimeter rock block with projectile that is being shot at velocities of 5 to 8 kilometers per second. And this is the material which is being lost by the fragmentation, in situ fragmentation, and radial pattern of fractures that emits with respect to the hit point. So this is the general view, and even though obviously in the modeling here the conditions are different in terms of rock type. Yes, please. This is gabbro, which is a hard rock. Okay, probably the most one of the famous sites, one of the bigger meteorite impact is in South Africa, the Vredefort site, and with a lot of peculiar features, which are fractures that called shuttle cones that I'll show you in a minute. The impact was about 2 billion years ago in this area. It generated a disturbance, an effect of a radius of about 100 kilometers or even more. Today the scenery is quite scenery, and these are rock blocks that are being elevated. This is a granite quarry. The black material is a melted rock, just that formed this with the nice name of pseudotacholites. And this was a very natural place to go because of the exposures are quite nice. The center itself is not exposed, but the exposures in the green area is where we went to. Amir, Jay, and myself went there. I overheard Jay complaining to Tamar that we tried to convert him to geology, but we didn't succeed. But he enjoyed the South African steaks every evening. So,
morning wake-up call. You were converted to geology.
To a very large extent, you're right. And well, the major job was done by Amir, and Jay was just the mediator. So what are shuttle cones? Shuttle cones are very peculiar features. They many times appear as quasi-conal shape. They have a special striations on them that I will show you in a close-up in a minute. And they are found only on Earth, only in on areas of cratering, meteor cratering, and they are not found anywhere else naturally. And they were not understood, but they remain enigmatic for many years. And even though they are considered to be a very clear indicators of meteorite impact. So what I show you two samples in two different rock types from South Africa. You see this Ostale. The term is Ostale. You see that there is a branching, a V-shaped feature that I'll come back to it, and this is quite typical. We also worked in a quarry in Indiana where the meteorite impacted the area 300 million years ago. For scale, this is one of the students in our trip, and this is a wall, and I hope you can see there are quite many horizontal fractures. We are close by, we see those fractures appearing, but if you noted, many of them show an angular branching. Here is another close by, and you can see quite clearly this branching on different levels. When you take an enzyme specimen, this is the surface before we broke. We take pieces, we see penetration of surfaces inside, and this is a cross-section with branching into it. So the first conclusion of the field work was that we're seeing a mega fracture. They appear in set. They are branching in 3 dimensions. They are not necessarily cone, they are quasi-conical, but very strong branching, and we interpret them as being tensile fractures. The question is, what are these striations? And this looks, there were essentially no attempt to explain those, and here it came that at about the same, somewhat earlier, the work of Eran and Jay, they found this a small perturbation on surface of a propagating rupture that was a physical manifestation of the fracture front waves that early on was predicted theoretically by Morrissey and Rice. And the basic idea is that if we have a fracture front propagating, hitting some obstacle or some impurity in the inside the material, then there is a front waves moving on, there is a wave moving on the front, supposedly supposed to be elastic, but yet it left indication in the rock. And basically, because this theoretically the wave moves very close to the Rayleigh wave speed, then by this angle one can calculate what is the velocity, and just from that angle. And Ran and Jay showed basically experimentally that this actually worked because they knew the velocity and they measured the velocity using this geometry. So it is a very simple formula that indicate that. And now we come to the question, okay, we see those V-shaped striations on the surfaces, and we make the hypothesis that this is basically a front wave, a fracture front waves, and let's see that. So we made this assumption, and then from this hypothesis we can make and we went down basically. Amir was working and taking the measurements of different locations from the center, and these are the angle that he found that it could reach values, calculate basically having a speedometer on that. Now, this assumption makes a prediction that when we are close to the center, the impact site, we will have high propagation velocity, and with farther distance, the velocity will reduce. And indeed, this is the distance in kilometers, and this is the angle for different 5 rock types that we found them. Everything is normalized by the Rayleigh wave speed of the rock itself. And we didn't see, because of exposure, we couldn't come closer than about 12 or 15 kilometers, and this is the last place where we could find those striations. So taking the angles, basically we find that Shuttle Cones forms at this range, 0.9 to 0.98 Rayleigh wave speed. This is a model from J. Melosh and collaborators in which for that site, the impact excavated a hole in the earth of 24 kilometers deep within 3 seconds. And this is the stresses that, this is the range where we measured our data, and these curves are the calculated state of stress from the model, and plotting using that curve on our data. Basically we see that the very fast fracture generated by at about 30 gigapascal impact loading of the shock waves. In summary, that's what we saw, that Shuttle Cones form only in very high energy situation, which is what proven by the virtue of the fact that they are seen only in meteorite impact, and they require very high energy, and the striations are basically speedometer of the velocity. Yeah.
Question. So, Rice Morrissey paper, the front waves were measured in mode 1, right? Do you have an idea of the mode mixity you have during impact? Because that could maybe explain the variations of front waves.
Yeah, that's a good point. We think that these are tensile, they form under tensile conditions. No, we didn't see any indications in the field, and basically we have a long debate at the time with Jay Melosh about that, and we talked about the tensile stresses in the backside of the propagating shock wave. So we envision these as tensile fractures and not shear. And now, following your request, we switch to shear. We know that earthquakes are driven by fault weakening, the difference between the preloading and during the release. And the question is, what controls the fault strengths during dynamic slip, dynamic both rupture and I'm afraid of Vladimir. We built a machine that can reach those velocities, some conditions here, and we succeeded in getting approval of J that even though this was just last winter. And okay, there are quite many parameters that I'll talk about this mechanism of weakening. As you can imagine, there's dealing with rocks and earth. There are quite many degrees of freedom and parameters, and the result is that there are many opinions. So I'm not going to cover the spectrum of opinions, so I'll stick to what I think is working, and not and I hope it's even not all of it. Okay, anyway, there are kinematic parameters of the weakening as a function of slip distance, slip velocity, and acceleration, and as well as rock types and environmental conditions, and this is a host of issues that difficult to integrate. So I'll try to focus on a few points. My view is that all the phenomenon of the fault strengths, not all, but most of the phenomenon of fault strengths during earthquake can be boiled down by nanometric powder that forms on faults, both in experiments and in the field, at basically even negligible displacement. Furthermore, I would very delighted to see the papers coming from the studies by Jay's group saying that friction is fracture. This statement cost me not getting a proposal from NSF about 15 years ago, because the second sentence in my, without knowing anything, the second sentence in the proposal was friction is fracture, and I was told afterwards, not by you, but a very well-known rock mechanicist, this is the killer of your proposal. Next time, try to hide it. So, and I succeeded a little bit afterwards. So, now, why is this important? Because number one, it's called gouge. It's a very fine grain at a fault. It forms, I said almost always, just as a disclaimer, but practically it's always. High strain rate associated with earthquakes promote this type of fragmentation, and I will briefly go through mechanisms how this can cause the weakening. I will not go, I will go very quickly on that. There is two zones, the rupture front, where velocities are the orders of kilometers per second, and the backside of slip velocity of about a few meters per second. The result is that the strain rates in the close to the tip are the order using a French calculation, and this is from Ilias' work. And here it's the strain rate is strong function of the thickness of the zone and the velocity. I'll show you some examples from experiment that we know the velocity and we know the thickness of the localization zone, in which the strain rate are the order between 10 to the 5 or 10 to the 6 per second. So at the front page, this is some calculation I did in the past. Basically, when the rupture front comes in, there is also variation between dilation and compaction, and this leads to intense fragmentation as known experimentally. This is experiments in which rocks at low, moderate strain rate are fracturing, at high strain rate are fragmented. And this is examples from two faults that we worked on. One is in a gold mine in South Africa, a fault, an earthquake of magnitude 3.7 generated quite many powder zones. This is a single earthquake. This is a San Andreas. This is a pickup truck for scale. A very wide zone of a gouge form, fine grain gouge. In this diagram shows the grain size in both. In red, the two curves show this is frequency and grain size. In both cases, they showed, ignore the blue one, showed that the two curves are quite similar. And what is most important when we look at the dark field in X-ray, we do see that grains, this is 1 microns, we do see quite many smaller nano-sized grain are being agglomerated together. I'll skip that one. This is from the experiments of coarse dolomite grains, and we get localization. This is a final localization slip during an experiment. This is 1 micron thick, and the grain inside is in the nanoscale. So let's see how the existence of this nanometric material could lead to weakening. One way is that the grains, because of the heat, are forming a very smooth surface on the sliding surface. So this is a AFM view. This is 3D. This is top view. The surface is composed of nanoscale grain. This is 2 profiles, one of them parallel to the slip direction and the other one perpendicular. This is perpendicular and this is parallel. There's obvious clear smoothing on here. And then using a spherical glass bit on the tip of the AFM, we can measure the friction in the slip direction and the scale of a few microns, and as a function of the measured roughness. And what we see here is the friction coefficient as a function of the RMS, or from other sources, the roughness. And what we see is that friction for dolomites and for granite, we do see as the roughness, as the smoothness, meaning the RMS smaller, the friction drop, and this exists in other measurements in granite and in diamonds as well. So smoothing, which is facilitated by the fine grain, leads to reduce friction. Another mechanism is that we found that facilitated only in a fine, or at least we found it only in fine, in the gouge, is rolling. And this is the development of rollers that made of the fine grains. So this is, we saw mostly in granite and diorite, formation of small rollers that are, here is a close-up of such a roller. This is 150 nano, and these are the grains that made from the small powder, forming this cylindrical structure. And turned out that these structures are very uniform in size. They're about 1 micron plus minus.
Sorry, rollers, they have some granite. What is their mineralogy?
Good point. The mineralogy is the same as the gouge from the grinding of the granite itself. So those rollers form during the shear, not independently. They are basically formed and destroyed during the shear. And they are oriented 90 degrees to the shear direction that we know. So basically, this is from Tabor's mechanism. We envision that the fault becomes a bearing, a roller bearing, and we take the model from the 50s of roller friction from Tabor. These are measurements. This is AFM measurement of the surface and the surface with a roller, and we calculate a very clear or theoretical weakening as a function of the presence of roller. This is a plot of the initial friction to the final the final friction as a function of the initial friction, with red of experiments with rollers, and in showing clearly drop of the friction, and in blue experiments without rollers. I don't want to be in fight with Vladimir. This is one important issue that I want to mention finally. Many experiments are done, and Chris Maroon mentioned it yesterday, in which the people take in the fault zone, they take gouge. They put gouge to begin with. Our experiments show clearly that the effect of the powder lubrication is only effective on freshly formed gouge, not on existing gouge. For example, here in this experiment, we take in a granite, we start at friction of 0.7, friction drops after 600 seconds to less than 0.3, quite steadily. This is typical for many experiments. Then we wait just to change the setting of the experiment. If we run at the same velocity, the friction slight rise for healing, and then it continues to drop, coming to the same steady state friction. However, if we switch to the lowest, to very low friction of 0.3 millimeter per second, it starts a small initial strengthening, but then while slipping, it's being strengthened. So there's a competition between the healing and the weakening. And because it's in the high velocity, relatively high velocity, the weakening wins. In the low velocity, the healing wins. And we come back to almost a friction of 0.9. So basically, this is the view. We start with a rough surface with some gouge. We continue shearing. Gouge is being formed. Localization inside the gouge, and then friction drops strongly. And I don't have the time to go into it, but in granites, we see phenomenon that as the velocity and time passes by, we get strengthening after significant weakening. That I talked about this with Shmuel a day or two ago. Thank you very much.